Thank you. I came here just to, I haven't been doing much K-theory lately, and I was wondering, but I came here to learn it, but then I was invited, thank you, to speak, thank you. So I think Christian told me that application of K-theory to number theory is more or less finished. No? Okay, it was not wrong interpretation. Okay, I talk about things over function field. So I just give some notation to do anything. I work over a curve over a finite field. Geometrically connected, and I fix a closed point and functions like this, and I'll have this completion at infinity, place infinity, and this is the completion of the algebraic closure. So I'm thinking an analog like, I forgot to mention K, which is the field of fractions, which is the function field. And this is, this is the field of fractions, and I have R and I have C. And so the aim, to try to make it sound big, I will say that the aim is to construct elements in, maybe it's called zeta elements. So this was an older result, improvement of an older result. So this is about zeta elements in, say, motivic cohomology or K-theory of, say, motives over K. So the tools I use, actually, I just look at Drinfeld modular varieties, Drinfeld modules. I will try to give a definition later, but giving a definition now is not, I don't find it helpful. So I'll just say that there are ranks, various ranks, and the analog here is the group scheme, GM, is the analog of rank 1 Drinfeld module, and this is rank 2 is elliptic curve, and it does not apply here for bigger ranks. And I will be working with moduli spaces of these things, of, say, of level I rank D, and I will write of rank D, I will write of rank, this is I, A, and A. And so, the moduli of this thing is actually spec of the ring of integers of cyclotomic fields. So I here is an ideal, and the analog here is just NZ. And for elliptic curves, you have the moduli scheme, you have the integral model over Z, and these do not apply for higher ranks. So the common feature is that these things are A schemes of dimension D, and these are regular and affine. So I'll be looking at motivic cohomology and K-theory of these varieties. So so the talk will be survey-like, and why do we consider this is because the cohomology of these varieties realize a Drinfeld of say, it's all cohomology of I guess it's not, you also have to take the sum, but of these varieties, let's just say, or the limit, this way. There is a Galois, I'm sorry, I will take this to be k bar, which means that I'm tensoring this to the algebraic closure so that you get the Galois representation. And you can also identify this space with to a certain subspace of automorphic forms, giving Langland's correspondence. It's partial. It's only partial thing because there is a moduli of Stuka which gives the full thing, not just partial. So assuming, I don't know, this is maybe too rough, but assuming at least the Tate conjecture, you can start with a motive, and you can take the, I don't know, étale realization to get some Galois representation, and then you can use the Langlands to get some automorphic representation, and then you can see this as let's say pi f. Then this is cut out. This is a rough story cut out by Hecke correspondences cut out by from these varieties. So in principle, we are looking at, by studying just the Drinfeld modular varieties, this sort of, I don't know, appears as a part of. So this is why we work with this particular Drinfeld modular varieties. Now, so this is of course an analog. Maybe this remark should have appeared earlier. This is an analog of Shimura variety. Okay. Yeah, the thing is, there are no Shimura varieties of GLD for number fields for d greater than or equal to 3, but over a function field you do, and you can work with them. So the interest, so there's Baileinson's conjecture, and this is something about proper smooth varieties over Q, and I'm just going to say that this describes, this thing. In terms of say orders of L function of X, or the lean cohomology, and this thing is, for example, the image of the script X restricted to this X, where this is the integral model. a nice integral model. This is regular and proper flat Cartesian. So, but in general, definition is due to show uses alteration. So I'm interested in the function field analog of this. Before I say that, I should remember, so this conjecture is not known only for maybe dimension 0, and there are some partial results in other cases. I'll mention one. Beilinson. And so this is the case where this is the modular curve. So this is without the cusps, and this is with the cusps, the compact curve. And in this case, they construct elements in what's called Beilinson elements. In this is 2. And they prove that this is as larger than let's say the dimension of cusp forms. With so there's level and there should be a level. I'm not going to make this precise, but so this is the order of L, or it's in this case I think it's equal to the dimension of eta cohomology of some twist. So this is the I want to talk about the analog of this result.
Sorry, I'm not quite understanding it. Are you saying that's a counterexample to Beilinson conjecture because it's too large, or are you saying Beilinson conjecture you should expect it to be larger than that number?
You expect it to be equal, the order and the dimension, but you can only prove that it's bigger. Because, yes, it's at least.
Okay, sorry. Yeah. Go about. Okay.
There is no finiteness way to. So I have to erase this board. This is our main theorem is about K-theory of Drinfeld modular varieties. This restricts to over K, to K-theory over K, and we have a certain map called Regulator. And this goes to, say, automorphic cusp forms. Actually, I now think, well, cusp forms with the level, it's a fixed part by this group. This is a subgroup of the finite adels. Finite adels is, in this case, this, and A hat is not the finite completion, but it's an analog. It's the analog. And for here, I also need to say cost forms F such that the corresponding automorphic representation, the infinity component is isomorphic to the Steinberg. So this comes up when you're working with the Drinfeld modular variety, and this is the reason why I say that Langland's correspondence is only partially realized. This is a restriction. And I'm not going to define Steinberg, but Galois, corresponding Galois representation is the extensions of these things. Maybe it's the.
Could you say again what is the statement of the theorem?
Oh, sorry, I did not say it. I should say, so this map is surjective. So this
the top map or
this composed map. And the older theorem is the rig is surjective. So there's an improvement. So this is something like cost forms and corresponding objects here. I will remark on the regulator map, what the regulator map here is. So this is, we use the uniformization, use rigid of the modular variety. So this is like the complex points, and this can be expressed in form like this, where so this is an equality of rigid analytic spaces over K infinity, and omega d is I mean this does not help, but it's just hyperplanes. Rational hyperplanes. So this is an analog of P1C minus P1R. This is an upper and lower half plane. And so using this uniformization, and gamma I are something like congruent subgroups of congruence subgroups. And using this uniformization, I have the map starting from the K-theory of the moduli, and I just take the analytic thing, and then I use the canonical covering of this thing. There is a nice covering by aphenoids. And then I take the boundary map successive. And comes to a point which is just Z. And so this product refers to a canonical covering by aphenoids of the symmetric space. And these are, so I'm not going to define it, but I will just give a picture in the case d equals 2. So this is the tubular neighborhood of the tree you see it in your book of buildings, or book, I guess I saw this in a book by Serre. And this regulator in this case is something like, so aphenoid, the picture of the aphenoid is like this. And if I take the boundary, I get 2 points removed from P1, 2 points. These are 1.2 points. And then I go to a point, which is Z. And so these points and cover. So this is an aphenoid given by, I think, the field with T1, T2, T1, T2 minus pi or something. Is this right? Yeah. So is it correct? No, maybe. Yes, I removed certain hyperplanes and then consider this. Consider the. Oh, yes. But I remove these points and go to this component. Oh, thank you. Yeah, so I thought maybe, so the title of the next talk was rigid analytic, K-theory rigid analytic spaces, but this one is a naive one. One more remark concerning the motivation. So there's Parsons conjecture, which says that Ki is rationally 0 if this is a projective smooth over a finite field. And this is related in that, so in favorable cases, I start with some motive over K, but we want to consider the integral thing over A. And suppose we have a model over C, and let this be the special the fiber at infinity. Then we can consider the localization sequence K of C going to, I'll use G theory. And then these are 0 by the conjecture. So you expect this to be close to isomorphism. And actually I'm considering, I said I take successive boundary, but here this is the idea regulator. This is where the idea comes from, and actually this is the very first idea was I found in Kato's paper for surface, that the boundary has to do with the regulator. Actually, I can say I will make some more remark. So this is a talk with many remarks and not so many proofs. But Manin says that if you have a variety over Q, then this is regarded as a totally degenerate at infinity. I don't know where I should put the quotations, but so I'm giving if this is over a non-Archimedean local field, maybe I'll use Y, is totally degenerate. This is definition. Yes, one definition is that Y has semi-stable reduction with the components. All the components are Pn, where n is the dimension. So this is the case. In our case, it is. So in our case, it is AK at infinity. So these components are Pn. So the boundary maps are easy, and also you can see that this K theory of this special fiber is close to say it's a tau cohomology via the weight spectral sequence. Yes.
So you're somehow like your boundary goes into the product of set.
Yes.
But it's supposed to be going to some homology of the dual complex of this special fiber.
Yes.
So I don't know. I mean, so just maybe more precise picture, isn't it?
Yes. It's the harmonic cochains on the building is one way to say it.
That's the Brooks way, GS way.
Oh.
But like I think this you can also like define this I don't know. Can you define this in a more refined regulator map? I mean, there's into this some kind of a homology of this dual complex of the special fiber.
Yes.
So that's somehow like this target space is too big in a way. I mean,
With the product, you mean? Yes. It will go to It will satisfy certain harmonicity relations. Okay. So totally degenerate case, the boundary map is close to a tau cohomology, and I don't have it, but is this boundary regulator or boundary is the Chern class. I don't have this abstract or better definition, but this can probably, I don't know, maybe this can be worked out. This one I don't know how to do, and so the problem is that this variety is affine and not proper. So the wish here is that there exists a compactification I don't know, some nice compactification for which this type of surjectivity holds. So there's a map from the K-theory of this, or the integral. I also need some integral model, and then you can restrict it to, I guess, the source of the map there, and then if you compose it, it's still surjective is the question. So for this, so the remark concerning this wish there is that there is a compactification, but I don't quite remember what kind of compactification this is. Compactification. And we thought about this. So even if we have a compactification, nice compactification, for example, if the boundary is stratified by, say, the moduli of lower ranks, I still don't know. So maybe if we have, if say something like the finite generation of K groups hold. So in the case d equals 2, this was done for modular curves, and the similar method applies. But even for d equals 3, I don't know how to do that.
So you don't know what exactly?
So the way for modular curves, you construct an element in the open part, and then you want to extend it to. You first construct things here, and then you want to find something here. And in principle, you can do that because these are cusps. The difference are the cusps. So if you look at it in an automorphic way, they are distinguished by Hecke correspondences. But if these are not finitely generated, I don't know how to pick out the cusp part or the Eisenstein part. So this is the part about the Bailinson type theorem, and I go on to now to the norm compatible part.
So you are
Mm-hmm.
So the boundary of them doesn't vanish. Boundary to the K1 cast.
Here, you mean?
That's your problem?
Yes, yes.
I see. So somehow you have to adjust.
Yes. And this is done using Hecke operators in the classical case. So I'm not going to give the definition of Euler systems. Actually, this Euler system is different. I use these, and these are not the true Euler systems in Iwasawa theory. So it might be, that's why I made the title to be norm-compatible systems. I just call them Euler systems in my papers. But so I just give the definition. Cyclotomic case it's the system of elements in, say, some cohomology theory. In this case, I take this to be indexed by the levels. And the norm-compatible property means that I have NP, N, and these units, these elements can be computed. The norm of these elements can be computed, and they come to something applied to the element downstairs, and these are different when this is prime, and these are prime, and these are not. These are coprime, and these are not coprime. And this part is the L factor. So this is what I mean by norm-compatible systems. And there's another example in the case K2 due to Kato, but actually I'm finding the proof hard to believe now. I don't know why. He claims that he has non-compatible systems in this thing, but I think it's safer to assume tensor Q. And if you assume tensor Q, then many of the applications do not work. So I don't. But I don't know. Maybe I'm just confused. I cannot follow the proof. I don't know if. So there's a symbol map, and let's say you have the finite quotient, and there's a push forward, and there's a norm map. And this is not, I don't know if this is commutative for the case where you have like modular curves. Is this commutative? I just want them for, say, modular curve and their finite quotients by some level, natural, but I don't know. And if I have this commutative, then there's no problem, but I don't know. So our theorem is, our older theorem is that we have norm-compatible systems in this K here, but tensor Q. And our theorem today is that this is in MIA, but with motivic cohomology. So remark is that these examples 1 and 2 have applications in Iwasawa theory. And this example 3 with d equals 1, there's some analog of Iwasawa theory. And for d greater than or equal to nothing, or we don't know Iwasawa theory. But this was used actually for the proof of previous theorem, not this theorem, but previous theorem. So I use that you get the Euler factor there. I forgot. I was going to write some more about Kato's Euler system. I should do that. Maybe not. I'll skip it. So this is introduction. This is the introduction. I sort of made the statements of my theorem, and I'm going to give the construction of elements in here. This is not too difficult, but it involves like a definition of Drinfeld module, and this is not so pleasant, but I'll just make it quickly. So, yeah. So, I mean, with these elements, you sort of get all the elements you want in motivic homology of, say, motives over K. So, let's see how it can be done in 20 minutes. No, 10 minutes. 20. So, rank D equals. So a Drinfeld module. So this is not so interesting geometrically. Rank D. I'll use the notation like this. Maybe I'll omit the phi. And so this is just a GA bundle. So it's an S group scheme. And you have the endomorphism or A action on this S group scheme. And this has to satisfy certain things. So this is a finite flat. Degree is equal to the valuation, and this is where the rank comes in. And another thing is that there is an action on the Lie E by this phi and also by the structure map, and they coincide. So this is the definition, but I will just give an example. In the simplest case, where this is the affine line, and so then if we take the base to be spec of K, this is just spec of KT, and the endomorphism ring of E is equal to the notations like this. So this is a commutative, non-commutative ring with the relation like this. Okay. And tau is the qth power. So giving a ring home like this from A to the endomorphism ring is determined by the element phi t, and the part about the Lie thing is reflected like this. And the part about the rank is reflected like this. So rank 1 Drinfeld module is just given by this data, for example. And I also need torsion points to define level structures on elliptic the Drinfeld modules. And by this, I just mean the kernel of this A action, or maybe this is, I should say, phi A. And for an ideal, I just take the intersection. So for example, the torsion points of this example, this Drinfeld module is just the roots of Tx in K bar. So these torsion points of rank 1 Drinfeld modules generate abelian extensions, and they give it's a class field theory partial. Okay, so with this definition, no, actually I need to define level structure for general torsion A module. Level structure on E is a morphism like this, A mod, such that the sum of is a closed subscheme. So this is slightly more general than the usual one where you have just the isomorphism. I was going to give it, but I don't have time to write it down. And the proposition is that actually this is something that we had to do, but this is representable. If you make the functor is representable, and I gave the properties like regular, affine, and of dimension D. And when for if the support is greater than or equal to 2, and so when the support is 1, actually the cardinality is 1, then it is a Deligne-Mumford stack. But I don't know anything. I never thought about what the motivic cohomology or K-theory of this stack should be. So I just want to give the construction of the elements, and so It's just, it's done, it's written first in Asahi's master's thesis, and it's, I guess, essentially due to Kato. And we need for the previous theorem, the level structure to be like this, but for simplicity, I'll just assume I equals j for simplicity. So to construct elements in K-theory of moduli, I will have, so I have the universal Drinfeld module over the moduli, and this is a GA bundle, and also the universal level structure And for each x, I have the map sections like this. And there are 3 steps to the construction. First, you construct theta function. I'll just let it denote by theta n. And this is an element in here. And the second step is to construct zero units, which is denoted gx and is defined to be the pullback of theta. And this lies in the units when this does not intersect the 0, because it's a unit away from 0. This should be 0. And then you just take the product of the simplest possible basis-like thing. So n is just the copies of AIs, A mod i's, and I just take the product like this. And this lies in K group. And similarly, I can define the product using the product of motivic cohomology. And these are just in so these are the elements, but this is not still. This is actually not enough to generate the automorphic forms, all the automorphic forms. But we also move. Okay, I should talk about what the theta n is. And in the example that I talked about, the simplest example, maybe that rank, it may not be rank 1, but when this is just over a field, then theta n is just some powers of this t, the coordinate function, times some element in this. So this actually is characterized by the divisor. I mean, it has the zero only at 0 here, and by the norm invariant property. These are the characterizations, and you get the power, and you get this unit up to q minus roots of unity. But I just want to say that this is just the coordinate function on this GA. This is as simple as that. And so the Ziegel units are just torsion points, pulling back by torsion points. So I said that these are the roots, right, in this case. So these are just the roots. And I need some more elements. This is like the best, easiest elements, but you also need to shift it by finite adels. So this acts on the rational K-theory when you take the limit. N. And then you can define things like gamma also in, and you can actually show that this lies in N. It's just moving by Hecke operators in some sense. So it's a pullback by finite map, and then a flat map, and a push by finite map. Yes, so then the proof is that the proof, it's not a proof, but so then these elements generate the surjects. This thing, so if you have gamma, I don't know if I can do this correctly. You can choose some finite cover of, say, mn, and then where it sort of factors through. I can't give the precise definition right now. Yes, it will give a algebraic correspondence like this. It's sufficiently big cover. And the choice depends on, there's a choice, and that's why I take tensor Q. Yeah, so if you don't want it to be, if you don't need it to be, say, well defined, you can just pick some algebraic correspondence, and then stay in without tensoring Q. But then that, yeah. So I want to give the precise, 1 minute. Yeah. What should I do? I'll just write down the statement and not define things. So the norm relation theorem looks like this. It's for the motivic cohomology. Yeah, I have to show this factor, I guess. So this is a norm map going from this level to there are two ways of taking norms, and this is the one by quotient, actually. This is the one induced by the canonical surjective map. And so this is the L factor. I'll just give a remark that this is a real, so if I add, so this is a L factor at s equals 0. So if I have add this factor here, and maybe replace this by Hecke eigenform by this Hecke operator, then this is the unramified L factor, local L factor for automotive form. Yeah, I did not define the Hecke operators, and I did not define really this M, but I think time is up. So there is a formula that we have a regulator of upper ij gamma, and if you couple it with, so this is the target space was subspace that like with the harmonic, then you have a pairing, and then you can compute it like, I don't remember the exact formula, but it's something like with certain factor. Finiteness of Shah? No, I don't think so. Yeah, that's not related to your remark at all. But I want to add that the arithmetic things are within. So we've done this integrally. So I think there's no arithmetic problem in this regulator situation, but the number theory interest lies in, I guess, in this map. This is, and this is isomorphic with Q coefficients. Gamma is some gamma I, which is, for example, some congruence subgroup in PGL. So this is discussed in paper of Kaya, Kato, Sharifi. And so what we are looking at, we start sort of from this point. So we don't look at this map. We just use the isomorphic. I mean, our theorem was about surjectivity tensor by Q.
Thanks, Satoshi again.